with Zoom meetings, and it seems that our lives got really busy somehow. I don't know how that's possible when we're not going anywhere. Some people are going places, but for most of us who aren't going anywhere, I just got busier. I don't know about you guys, but that's what's happened to me. Um, there's been a lot of interest in Portland limestone cements over the past 2 years, especially especially with the sustainability and the and greening of the economies. And so one of the things that I'd like to present on is one of the initiatives that we have in our industry, and the new product called Portland Limestone Cements. It's been around for a little bit of time. We got a lot more experience with it, and I just want to share some of that with you. There's a group of us in the state of Illinois who are responsible for, keeping the relationships and the conversation going. And so this is our task group, our Portland Cement Association task group. You probably recognize a lot of the people on here. And so I wanted to thank the guys, and well, there's no gals in it, but thank the people who participate in it. We have these organizations, these state communications groups, within each state. It's a different group set for each state. And if you have any interest, questions, follow up, you can always approach me, or you can approach one of the people that are up on the screen. We're getting a black eye. The industry is getting a terrible black eye. Unfortunately, we're in the crosshairs of a lot of organizations. One, The Guardian came out with this article that said that concrete was the most destructive material on earth. California is basically constantly, has the cement industry in its crosshairs, and rightfully so. It's our process where we have a lot of process emissions of carbon dioxide. It's inherent in the process, and that's not going to go away unless we change how we make Portland cements. So in the US, we're responsible for 1.5% of the carbon footprint, and that's the cement industry itself. Worldwide, it's 5 to 8%. Some people quote 7, some people quote 5, other people quote 8. I just framed it around 5 to 8. And there's constant pressure from environmental groups, designers, regulators, and the public want to know why we're emitting so much CO2, why we're contributing to climate change, and what we're doing to prevent that and to stop that. The problem is we can't really live without concrete. Concrete frames our infrastructure, concrete frames our homes, concrete's resilient, it's durable, it carries our water, it carries our sewage, it provides comfort, and we need concrete. It's an essential building material that is as the story goes, it's the second most consumed material on planet Earth per capita. So we have to do something about it. And in 2018, the Global Cement and Concrete Association was formed in London, the UK. And it's a group of companies, and I'm going to show it in a second here. And we realized that we're part of the problem. We're also part of the solution, and we're confident that we can achieve this global commitment. The global commitment basically says that we're going to continue to drive down the CO2 footprint of our operations, products, and deliver society carbon neutral concrete by 2050. It's only 30 years away. Of course, it's carbon neutral, so zero carbon. I'm going to show you the pinwheel in a second, but it's across the built environment value chain, which basically means it's in concrete, it's in structures, it involves a circular economy, and I'm going to explain that just a little bit too. And it goes through the life cycle of the building. Just as a quick comparative, if you build, anybody who has a wooden deck compared to a concrete driveway, you don't do anything to the concrete driveway or concrete deck if you have a deck. But you have to resurface and most often replace the wood deck, and it only lasts 10 to 15 to 20 years, whereas your pavements and your slabs are going to last 50 to 70 to 100 years. So you have to take it across that metric that you're using. You have to take it across the life cycle of the concrete, and that's something that we have to recognize, that it's not cement that we're putting down, it's concrete. So these are the companies, and you'll probably recognize most of the companies here. It's all of us worldwide have signed on to this commitment. It's real, and it's part of every company's commitment to net zero by 2050. So we framed it out. Some bureau, obviously in Europe, GCCA started in Europe, and they framed it out in what we call the 5 C's. So we call it cement, concrete, construction, and clinker. Actually, we break it out into clinker, cement, concrete, construction, and then carbonation is broken out separately here in North America. These are the 4 C's, I guess, then. So in clinker, I'm not going to deal with it. I'm not going to dwell on it, but we've got thermal efficiencies where we can achieve certain numbers. We've got low carbon clinker, biomass fuels, decarbonated raw materials. Carbonation construction is basically using higher performance concretes to get lower masses of concrete in structures to use less. Concrete can be improved by concrete mix designs to reinforce less prescriptive mix designs, to go more towards performance mix designs. The NRMCA is basically working hard to achieve this and to convince specifiers that that's the right way to specify concrete. And of course, on the cement side, we've got our work cut out for us. Clinker substitution is the biggest, it's the lion's share of the reduction that we need to go from, and the baseline is 1990 emissions of 783 kilograms of CO2 per ton of cement. Up to this point, to 2017, which is where they're starting from to get to their 2030 numbers, we've already achieved 116 kilograms per ton reduction in CO2. That's being done by process changes, change in the way we manufacture cements, different mill circuits, but we have a long way to go to get to zero, and these are basically the numbers that we have to try and achieve to be able to get there. So they broke it out, and right now we're adopting a 2030, so 10 years from now, we have a benchmark to get to. Similar things are going on in North America. Same framework is happening at the Portland Cement Association, and we just started earlier this week. We started with the Cement Association in Canada and the National Research Council in Canada. We're going to follow something very similar, a roadmap very similar to what CEM Bureau is following. And again, this is still CEM Bureau's roadmap, but they say in order to get to zero by 2050, they have to get to 472 by 2030. And the way that they're going to achieve that is through clinker, cement, concrete, and carbonation, recarbonation, and construction. And my discussion today, or my conversation with you, is basically cement, and 2/3 of that is through clinker substitution. The rest of it's going to come through electrical efficiency and renewable energy at the cement plants. That's in Europe, that's their job. We're coming up with the numbers that we need to do here in North America, but we know it's going to be a challenge. So a lot of us know right now, to get from this point to this point, baseline to low carbon binders in concrete, because it's concrete that we're talking about, right? It's not cement. You don't place a cement driveway, you don't place cement walls, you don't place cement slabs, you place concrete. And concrete is the material that we have to consider the end use. And so this is the point where we're at right now. Right now we use supplementary cementitious materials to replace Portland cement in concrete. So what used to be the baseline of 384 kilograms carbon dioxide per equivalent cubic meter, and this is meters here, we're reducing that by using supplementary cementitious materials, fly ash, slag, for example. But we can achieve another 10% reduction of the embodied CO2 by using Portland limestone cements. So in Portland limestone cements, I'm going to explain in just a minute, but in 2019, if we were to utilize Portland limestone cement instead of ordinary Portland cement, we would have saved 8 million metric tons of carbon dioxide, which is equivalent of 1.7 million cars off the road, enough to power 900,000 homes, and it's basically the carbon stored in 10 million plus acres of US forest. So uh, I mentioned earlier on that we shouldn't use the metric for cement. Cement obviously is a higher embodied CO2. You know, if you look across this one on the left axis, or the vertical axis, you'll see that, you know, there it is almost a 1-for-1 a ton of CO2 per ton of cement produced. It's actually 0.85 or 0.83 is the industry average that was calculated a few years ago, 5 years ago. And we're looking at redoing that right now. But when you look at it and compared to timber, we embody less energy, but we have a higher CO2 footprint, embodied footprint. Compared to asphalt, asphalt is a little bit, it's about the same as far as embodied energy goes, but you know, we're again, because of our process, we have a higher you know, carbon footprint, embodied carbon footprint. Still much less than plastics, bitumen, glass, steel is, you know, but steel is highly recyclable now. So it's, you know, it's, of course, it's viewed differently now, but it's not bad as cement. And it's, the story really is in concrete, where you have concrete, once you place it with aggregates, and, you know, cement only forms 15% of the concrete mix, then your embodied CO2 drops dramatically and your embodied energy drops dramatically. So we do have a good story to tell, but it goes to the total amount of material that's used. And because we're the second most consumed material next to water per capita in the world, that's, you multiply it by the sheer numbers, the amount of material that's consumed, and that's why you end up with the black eye that we're getting. So in the United States, we have several standards governing cements, type 1, type 2, 3, and 4. Blended cements, we have the Portland Pozzolan, Portland slag cement, 1P, 1S, Portland limestone cement, and then the ternary cements. They allow for pozzolan, slag cement, and limestone. So the blended cements is really where 1L resides right now in specifications. Hydraulic cements, the C-1157 was purely a performance specification that was developed years and years and years ago. It permits the use of several different materials, pozzolan, slags, limestones, but doesn't specify the chemical constituents or the prescriptive requirements of the other two specifications. It really is more of a performance specification, and really hasn't been adopted, you know, or embraced like people had hoped. And so it still resides in the specifications, but it's not really, you know, used all that often. And C94 really, it has equal recognition of all of the cement standards. And then, of course, there are separate supplementary cementitious material specifications, ASTM C618, for example, or C989 for slag. So the blended cement specification has been around for a long time. It's been around for over 50 years. The C150 has undergone quite a number of changes over the past 20 years, 15 years. So 1992, 1157 came out with their first attempt to come up with something that was more environmentally friendly. And it still hasn't gained traction. Portland Cement has made some changes, you know, in the C150 realm. 2004, we actually were able to add up to 5% limestone addition. 2007 and 2009, some changes for inorganic processing additions was recognized, where you can use a slag, a fly ash, other sorts of materials, whether it's organic or inorganic, but just addressing inorganic. You can add up to 5%. So with limestone addition, with inorganic processing additions, each being at 5%, your gypsum being approximately 3 to 5, let's just ballpark it at 5. Now your clinker factor went from 95 to 85, and it's still not good enough to get where we're going to need to go, unfortunately. And as I said, blended cement's been around for a long time, 1967, so almost 50 years. So Portland limestone cements, it's a blended cement. with additional limestone content up to 15%. So right now the Portland cement specs and the blended cement specs actually add limestone, permit limestone up to 5%. But your Portland limestone cement is up to 15%. And it's a quick way to reduce the carbon footprint by 10%. It's suitable for buildings, bridges, pavements, geotechnical applications. And it is becoming more available throughout the US, and it is right now, it's readily available coast to coast in Canada. It's pretty well, it's almost the dominant cement in Canada. I think just this past year, it surpassed it. We don't have the statistics on it yet, but that's kind of where we're at. Oh, and the Portland Cement Association actually has come out with this website that it's called greenercement.com, www.greenercement.com, where it actually has some background information, has some field tests, has some calculators. Well, I say calculators. It has some background information. It has the information, we hope, that will enable you to promote the product and use the product better. So Portland Limestone Cements has a really long track record, not that long here in North America, but it's been around since the 1960s. And they've used upwards of 20% in their specifications in Europe and in South America. Across the world, it's a very prominent cement. North America is kind of the last place that has adopted the use of Portland limestone cements. Canada adopted it in 2008, and so it's been in place for about 12 years. And the U.S. standards put it into play or put it in the specifications in 2012. Some of you may know that it was actually marketed as an 1157 prior to 2012 for about 10 years before that, probably in Western, most Western states. A 1L cement was sold as a GUL, or I believe it was a GU performance cement, and marketed for a number of years, but now it's found a home in C595. So going back to the Canadian exposure to it, it came in 2008. And again, in AASHTO ASTM in 2012. AASHTO and ASTM are harmonized these days. So it's pretty well one for one. Whatever happens at ASTM happens at AASHTO, and whatever happens at AASHTO happens at ASTM. We've got this joint harmonization task group to make sure that the specifications don't deviate that greatly. It makes marketing easier, makes the technical acceptance of products and processes across the spectrum easier. So in Canada, it's called GUL cement. In the US, it's called 1L cement. And as I said, it reduces the embodied CO2 by additional 10%. So here you've got a couple projects that were done in 2015. So 7 years after the introduction of Portland limestone cements in Canada, you got the Mattamy Velodrome on the left, they were both LEED silver projects. They were mandated to be LEED silver. In order to get that, they needed to meet certain requirements, but they also wanted to have GUL cements used as the sole cementing material in the project. So first one was the Mattamy Velodrome for the Pan Am Games. And then the second one here is the Toronto Football Club, Toronto FC Stadium, also constructed with GUL cement, also in 2015. But it wasn't all roses. At the very beginning, at the outset, we had concerns. Just because it's done in Europe and South America doesn't mean that we're willing to accept it in Canada. And as cement manufacturers and concrete producers, we had to make sure that we were doing the right thing. As cement manufacturers, we wanted to make sure that if we're promoting this product, that it's not going to give us a black eye. We wanted to make sure that it was going to perform. We wanted to make sure that it was going to be freeze-thaw resistant. We wanted to make sure that it was going to be, we were going to do the right thing by making it and promoting it. So we had to do our own work. And so one of the things that we did, Professor Hooton at the University of Toronto proposed a field site. and we offered up the field site to them. So we brought in an excavator, you know, that's Doug on the left here with a couple of his students after the hole was dug. And we put blocks in, we lined it with blocks. And that's the Toronto office in the back, in the background. They gave us a little piece of land here right by the railroad tracks. So real nice of them. But anyhow, we made it work. We lined it with blocks, put some framework in there to make sure that the material was going to be protected from above. And then, you know, Doug and his students ended up putting, you know, over 1,000 specimens into this storage blocks or storage field site, the vault, as we call it. And he has several different specimens. And this went on in 2010. So he's got specimens in there that are in calcium chloride solution, sodium sulfate solution, and magnesium sulfate solutions. In the hope of, Doug is a big durability expert on sulfate deterioration and damage, alkali silica reactivity too, but that wasn't conducted here. To Doug, he wanted a long-term storage site, so we provided it to him. The only thing we need to do every year is, you know, bring the loader out and the forklift and bring these specimens in once a year. Doug has his students measure them and they put them back in. So we got specimens that are 0.4, 0.5, 0.6, 0.7 water cement ratio, different levels of fly ash and slag, and in different storage solutions, and it's the one of its kind. There's not any more of it in its world and in the world, and it's been going on for 10 years. And then of course we just cover it back up every year until, you know, we have to open the tomb up again the next year. So far it's and I'm going to get into his results in just a little bit here, but mixed designs with PLC, everybody asks us, what do you do? Well, what our experience has been, and we verified it, that you just replace ordinary Portland cement at a 1-to-1 ratio. There's no compensating for anything else. We've discovered that you can use the exact same replacement levels of fly ash, slag, or other pozzolans without issue. Just like with any material, if you change a cement source, if you change a slag or a fly ash source, you got to make sure you do your testing. You got to test air, slump, bleed, set time, compressive strength to make sure that everything is dialed in. But typically if you're on the one source of material and you convert to another source that's PLC, there shouldn't be an issue. Most producers have reported no adjustments. We've heard, you know, from some that there might be a slight admixture dosage adjustment for slump, but other than that, it's been kind of a flawless sort of change. But like I said, it took years to do it. I mean, we had to build that site, that field exposure site. We had to do a lot of test pavements, and we had to do a lot of barrier wall, flat work, sidewalks. We did a whole bunch of demonstration projects to convince ourselves that it's the right thing. Typical effects on fresh and hardened properties, workability. Okay, do we take questions afterwards, or Dan, right? I don't know if there are any questions or not, but.
No questions right now.
Okay. If you get any, you feel free to interrupt if you want. I'm okay with that.
Sure. Okay.
You know, fresh and hardened properties, you know, just on workability, there's no significant difference. Bleeding, because there's a higher level of fines, because limestone preferentially grinds finer than the Portland cement clinker, you have more fines in it, and you might get a little less bleeding. But most people say that the workability is enhanced by that. It appears like there's less bleeding and there's less workability, but once you start working it, then it finishes even better, they say. Set time, there might be a slight decrease in set time, only because you're optimizing your particle packing, your particle fineness. Cement filling the gaps, or sorry, limestone fines filling the gaps between Portland cement particles. Heat of hydration, we really haven't seen it. You know, we thought that we'd see an increase at early ages, but it's really not that measurable, and it's not that much of a difference. So, you know, you can use it in mass pours, similarly to Portland cement. Compressive strength, uh, you know, it's all within the variability of the test method itself. Although the slide says can increase slightly both early and long-term strengths, it's comparable. We found comparable performance. We've had some guys who say, oh, it's a little bit less, and we've had other people say, well, it's way better. But you know, on par for all the testing that we've seen, it's you know, one for one. It's a direct replacement. Freeze-thaw resistance, you have a good air void system, good water cement ratio, it's not a problem. And sulfate resistance, poslins to use to get increased sulfate performance, sulfate resistance. And you can do that with Portland limestone cements just as well as you can do with ordinary Portland cements. So they actually work the same. Although it doesn't say it here, and I've got a graph on it, for alkali silica reactivity, it's the same thing. There. Just on its own, the specifications actually allow you to use a 1L cement as an MS as well, a moderate sulfate resistance, similarly to a Portland cement, and you can have high sulfate resistance just as you can with an ordinary Portland cement, or you can have a low heat of hydration, 1L, LH, similar to having a low heat of hydration type 4 cement. Same thing with moderate heat too. So the performance specifications in 150 can be matched with similar performance specifications in 595 or M240 for AASHTO. The other thing for placing, finishing, curing, as I said before, the handling is really the same. There really is no difference between ordinary Portland cement and PLC in concrete mixes. I'm just going to go through some of the hardened properties. We've got so many studies on this. I just pulled out just one of them. It was Doug Hooton and Mike Thomas's data on, you know, the scaling and compressive strengths, et cetera. But really for different replacement levels of slag, it's hard to see on this graph, but if you've got 25%, you've got, and these are in megapascals, it's a difference of 1 MPa, a 0.2 MPa difference, 2 MPa difference, half an MPa difference, you know, at 3, 7, 28, 56, and 91 days. I think they're 91. Maybe it's something else. I can't really read that, but it's similar across the board for 0 replacement, 25% slag, 40% slag, and 50% slag in this particular graph. So early age development, this is without SCMs. Portland cement is in the blue. Portland limestone cements, and this was a 12% Portland limestone cement content. Without SCMs, it had a little bit higher strength in this particular one. With slag at 35%, it had a little bit better performance, and with fly ash at 20%, a little bit better performance again. 7 days, it carried all the way through. You know, I wouldn't hang my hat on the fact that you're going to get increased strengths all the time. My experience has been you get equal performance. So this is basically saying that you're getting equal performance. It just so happened in this particular test that the Portland limestone cement had better performance than the Portland cement, which you might find, but you know, it should be equal. That's our goal. Our goal is to grind them and optimize the grinding, the intergrinding, and the gypsum addition to maximize our efficiencies in the mills, maximize the limestone content, but still get equal performance. And at later ages, the same thing happens. You know, you've got equal performance, same for no SCMs, 35% slag, 20% fly ash, and at 56 days, the same thing. Increased performance for Portland limestone cements, and for the 20% fly ash, just slightly diminished in this particular one at 56 days. Permeability, the C1202 or the T277. Without SCMs, you're going to get higher permeability numbers. Always do, because of the pore solution, your calcium hydroxide pore solution. That's known. But once you start adding pozzolans or supplementary cementing materials, you end up reducing your permeability to levels where you can meet specification requirements. So at 28 days, it's comparable at 35% slag below 1,000 coulombs for this test. This is at 0.45 water cement ratio. What was 2,500 coulombs is now below 1,000. And with the 20% fly ash, it's about 1,250 and 1,400 coulombs with the PLC and the PC. And 56 days, it doesn't really drop that dramatically for the non-SCM mix. Water cement ratio obviously plays a part in that, but just by adding in some supplementaries with PLC and with OPC, you get the same thing. You get equal performance and permeability mitigation. Scaling resistance, they're equal. In this particular case, the one with PC and slag actually had higher slag or higher slab defects, and the one with PLC had slightly less. And of course, they're all well below the mass loss limit anyhow. It's I believe it's 0.8 and 1 kilograms, so 1,000 grams and 800 grams is the limit for 50 cycles of exposure. And they, with the fly ash, the same thing with the PC. That one particular, it worked a little bit better than it did with the PLC for this fly ash, but still they're well below the limits that are permitted in 672. 666, kind of comparable durability factor, almost 100 all the way through, whether it's a PC, Portland cement, or Portland limestone cement. This was just a 1-year shot. I don't have the update for, this is like 10 years ago. Actually, this was done. This trial by the guys, by Houghton and Thomas, was done in Quebec in 2005, even before it got into the specification in 2008 in Canada. It was done in Quebec, and so that pavement's been down, and there's been no reported issues with it. Portland cement, and they basically just kind of abutted against one another. Portland cement with slag, or I believe it was fly ash here actually. No, it was slag. Sorry, Portland cement and 50% slag, PLC and 50%, PLC and 25%, and PC and 25%, and no scaling issues whatsoever. Anybody who's been to Montreal knows they get freezing rain, they get cold, they get snow, and it can be pretty nasty sometimes. And then ASR resistance, you get good mitigation with in your concrete prism tests, your accelerated mortar bar test, and your accelerated concrete prism test, which whether they were trying to promote at one point, it's still in the research stages, but equivalent performance, in ASR as well. This is for, I can't read that stupid thing. Hang on a second. Stop it. I'm gonna go back. I can't read what it says up top. My screen is, what is that one? Give me a second here. My menu is on top of it and I can't get it off.
It says PLC and sulfate resistance.
Oh, sulfate resistance. There you go. That makes perfect sense, because typically with, and I showed that already with sulfate resistance, if you put any sort of mortar bars or paste bars into a sodium sulfate solution, it's going to skyrocket. I mean, they typically do take off. Whether it's Portland cement or Portland limestone cement. But once you start adding supplementary cementitious materials that consume the calcium hydroxide in pore solution, you just get, it flatlines and you get below the maximum required to demonstrate that it's resistant to sulfates. That was the reason why Doug wanted the field site in the first place, was demonstrate. His big concern was sulfate performance and sulfate resistance. And basically, how do you order it? Is it available? The only thing, again, I said, and it's true. It's just a replacement of 1-to-1 OPC with Portland limestone cement. Same suppliers that you use for your ready mix operations now, same delivery placing equipment, same pneumatic tankers, et cetera. The only thing that we had as an issue was logistics. You know, you got to get it from the plant, you got to separate it out, you got to get it to the terminals, or you got to get it to your customer who needs a separate silo for it. We have co-shipped product with both products. You know, Portland limestone in one, you know, load, and Portland limestone in one and Portland cement in the other, and they co-shipped the same job because they had to, they had no choice. And at the end of the day, the concrete finisher didn't even know there was a difference in the concrete. He finished it all 500 meters from one plant, 500 meters to another, and didn't have an issue with it. So it's really, it's just logistics in separating out the products and making sure that you're sending the customer what he needs, right? So just some simple calculations that I did with our ready-mix affiliate in Canada. They've been the most progressive, although the entire industry is moving that way right now. If I use the EPDs, Environmental Product Declarations, from the Cement Association of Canada, we did establish an industry average of CO2 per ton for GUL and GU, and the difference being 85 kilograms of CO2 per ton of cement is a differential. And I just basically took the numbers that CBM has used over the past 3 years, and we basically, CBM in their usage of GUL cement basically saved 6.9 million kilograms of CO2 from going up into the atmosphere. 8.9 in 2019, and last year was just absolutely stellar. Almost 20 million kilograms of CO2 was prevented from going up into the atmosphere. In effect, it's in the past 3 years, over 35 million kilograms, or 35,000 tons of CO2 was prevented from going up into the atmosphere. So, and that's just one client, one customer. That demonstrates that hits home. So we've had some end users actually ask us, okay, if I were to use this material on a particular job, what would I get? And so, Ellis Dawn, I think this is Ellis Dawn, has a project going on. It's the wastewater treatment plant in Hamilton. They use GUL entirely for the project. It's 23,000 cubic meters, or 30,000 cubic yards, with slag replacements 30 to 45. And there's a YouTube project update link on this. Another big project that's going on right now, the healthcare, West Park Healthcare Center. Again, GUL cement with slag, 45,000 cubic yards being used in that one, 10 to 50%. Depending on the application where the concrete is going. And so, Ellis Dawn wanted to know, hey, if I were to use 25,000 cubic yards in a 5,000 PSI mix, what am I saving by doing this? And so the Slag Cement Association has a calculator. It's a verified, certified. Pretty soon, by the end of this year or the middle of this year, we are going to have everything in one location. I believe the Slag Cement Association calculator is going to have, instead of just Portland cement in it, it's going to have Portland limestone cement. But until then, you got to use two different calculators. I hate to say it. So the guys asked me, hey, if I use 25% slag or 35% slag, what's my carbon footprint? And so the environmental impact is your CO2, your embodied CO2 in this mix with zero slag is 392 kilograms of CO2 per cubic meter. This is per cubic meter. Oh, per cubic yard, sorry. And if you use 25% slag, it's 312 or 313. If you use 35% slag, it's 281 kilograms CO2. We know this one already. Everybody's able to use SCMs to lower it. But what if we were to take that particular mix and, you take your this is from the greenercement.com, the CO2 calculator, by the way. You can actually see if you use PLC, or replace PC with PLC in your mixes, how much more kilograms will you save? Well, for this particular one, 768, you'll save an additional 28 kilograms. For this particular one, 576 Portland cement constituent, you'll drop an extra 21 kilograms. And for this particular one here, they're all about 10%, of course, right? This one's about 10%, 18 kilograms. So your 281 drops another 18. So in essence, you're in going from your pure mix, your baseline, to just going to PLC, you drop it by, as I said, 28 kilograms per kilograms per cubic yard. In going with slag, you drop it even further. So if you were to go with your mix, your baseline 391, to go to PLC with 25% slag or with 35% slag, you basically end up with, in 25,000 cubic yards, you will save 700 tons of CO2. That particular job will get 700 tons of CO2 saved. 25% slag will save, over the baseline, will save 2,500 tons of CO2. And if you allow the performance specifications to rule, you could go with 3,200 tons of CO2. These are metric tons of CO2 per cubic for that project. So there's another link here, and I'll share this. You're welcome to have this presentation after. But if you go to the EPA equivalent CO2 calculator, which is also on the greenercement.org website, saving 700 metric tons is the equivalent of taking 151 passenger cars off the road for a year. 2,500 tons, which is the equivalent of this one, is the equivalent of taking 540 cars off the road. Going to PLC, OPC to PLC, saving 3,200 metric tons is the equivalent of taking 691 cars off the road or driving almost 8 million miles of a vehicle. That's what you save in making adjustments to your mixes and permitting PLC to be used. Just a few little highlights, some stuff that's going on right now. There's a big project in the Portlands area in downtown Toronto on the lakeshore. Of course, everybody in Illinois knows that the lakeshore is high dollar area, right? And you'll do anything to make it work and put condos on it. So they do the same thing in Toronto. And we're in the process of doing caisson work right now. So they're putting a whole bunch of caissons in this Portlands area, and that's kind of what it looks like, now. But what the hope is they're actually going to put condos on it, living space, cycling area, wetlands, keep some wetlands area, and some boating area, little retail, commercial, residential, multi-use condos. So what used to be an area that was really non-desirable is now becoming very, very, it's going to become very popular. And it's all GUL cement, Portland limestone cement, that's going into that project. It is approved in most states, and it's approved in the state of Illinois and accepted. You just have to change the specification and state that you're going to be using a C595 1L cement versus a C150 type 1-2 cement, or an ASTM C or type 1-2 cement. As I mentioned, the greenercement.com, www.greenercement.com, CO2 calculator is on the website. You can see the benefits of PLC, talks to you about it discusses some of the things that I talked about, has case studies, industry partners, contact an expert, contact me too if you want. I'm not an expert, but I'll do the best I can. And if you want more resources, there are lots of resources to get you where you need to go. And I think that's it. So I think, I'm not even sure how I did for time, but I'm pretty close to the time that you wanted me to go, Dan. And I'll open it up to questions if anybody has any questions about PLC and its use.
Yeah, thanks, Nick. It was a great presentation, and we're doing pretty good on time. We have about 10 minutes left. There have been some questions in the chat box, and I think we've covered some of these, but we'll just go back and make sure we have them addressed. Paul asked if there's any info on the 12 to 14 hour strengths. related to, you know, pulling post-tensioning the next day, jumping forms, that sort of thing?
Yeah,
I know
well,
you had,
you know, on the early age strengths, you're freezing. I don't know if it's my reception, I think I got the question. The question is earlier than 1 day, you know, 12, 14-hour post-tensioning restraints.
yeah.
What we found is we found, I didn't expect it. We actually found improved strengths over the over OPC on one of the products that we're manufacturing. We haven't done it on any of the others, but the mix design itself seemed to just replace it 1 for 1 and got better performance. In fact, better strengths. Again, it's equivalent at all ages. You know, we are doing some trials with precast cements, you know, high early cements as well now. And we found the same thing. It's a 1 for 1 replacement.
Great. There's another question from Mohammed about the limestone and whether or not it aggravates the ASR reaction. I think you touched on that, but do you have any further comments on PLC and ASR?
Yeah, we haven't found any indication that it creates a different scenario at all. It's as I said, it's a direct replacement. If anything, this is what some people have said. We haven't seen it, but they said that it should be diminished because you're actually reducing the available soluble alkalis in the system by adding, you know, interground limestone. You're intergrinding the limestone, so there's less cement factor in it, or clinker factor.
All right. There's another question about the max replacement percentage. I'm assuming he's referring to the maximum amount of limestone you could put in a PLC cement.
It's 15 right now is the max. So we don't want to have a 15%, anything over 15% out there. So we typically target something a little bit lower, and we base that on our weighing mechanisms and our feedback loop at the cement plants, right? So we look at standard deviations and we look at coefficient of variation. We basically set our set points in production based on what the end product's going to be.
Have you done?
There's a.
I was just going to follow that question up real quick. Yeah. So 10% is pretty common. Have you done? Are there projects out there with higher replacement rate?
Actually,
ratios, you know, in that 12, 13, something like that.
Yeah, in Ontario, what they're using, they are using higher than 10. In Ontario, one of the plants is set at 13.5. I think they're both set at 13.5. So all the stuff that I reported on, that's going on in Canada, all that stuff is like anywhere between, you know, 13 and 15.
Okay, thanks. Anything in the U.S. with that level of percentage?
Well, right now, the product that we're making out of the Charlevoix plant, and I think, you know, some of the others may be under the same restriction, because some may or will go to Wisconsin. We got to keep it underneath that 12% number that Wisconsin's got in place. So until that spec changes, we got to keep it at that point. But you know, I'm sure that once they change and accept 595 wholeheartedly, then, you know, we'll be able to move that upward. And the reason, I can tell you the reason why it's there, that was the very first state that we visited in the US to discuss the adoption of Portland limestone cements. I was in the room. I was part of one of the guys who did the presentation. And at the time, we were very conservative. As a cement industry, of course, we're really old school, right? When you're building stuff that costs you $500 million and $1 billion to build, well, you don't want to screw it up. And so we basically just said, we're going to produce to 10%, period. That's what we said. We're going to let it go. We're going to do all the research on it. We're going to study it. And at that point, you know, we had to optimize the mills. We had to make sure that the guys were, you know, adjusting the separators correctly. The ball charge was optimized. I mean, there were a whole bunch of things we had to do at the cement plant. So that's the reason why it's in there. There's no other reason why that exclusion is in there for 12 in Wisconsin, other than it was us who set it there in the first place.
All right, we have a few more questions here. Laura had a question about PLC concrete might be more susceptible to the Falmacite form of sulfate attack. Is there anything new on that?
Yeah, it's there's no evidence of that at all, and that was Doug's big thing, right? Doug and Mike Thomas, both those guys were insistent that Thomasite might be an issue with finely ground limestone, and that's why we built that field site. And the field site actually has thermometers in it. I didn't explain that. The reason why there's insulation on the top is so it doesn't get to freezing, but it actually controls the temperature to around 5 degrees Celsius year round. And that's what Doug was looking for. That's what those researchers were looking for, but there's no evidence of it whatsoever.
Okay, there's a, I guess, question comment here saying we have a push for carbon cure in the area. Do you have any comments on carbon cure?
It won't inhibit what you're doing with Portland limestone cement and supplementaries. It'll actually add to it. Carbon cure is just another way to add carbon dioxide. So it won't be a negative whatsoever into what you're doing with Portland limestone cements.
Okay, great. Monica was asking how the cost compares to Portland, just relatively.
Yeah, it's the same cost basically. It's not any more expensive. It's just another lever that you got to pull to lower the carbon, to have a lower carbon concrete at the same price. So of course I can't deal with price what the ready mix guy is going to do, but he may be promoting it at a higher premium. I don't know, but hopefully not. Hopefully all concrete goes this way.
And there's a question, does Portland limestone cement depress the pH of concrete?
No, pH is still sky high in those types of mixes. You really have to get it really to high levels of supplementary cementitious replacements to drop the pH down below where you get the passive layer on steel. So it's a non-issue.
Okay, great. That is all the questions we had in the chat box. Did anybody have anything else? Actually, it looks like one just came in from Peter, asking if there's any issues with durability, such as freeze-thaw.
Yeah, and we haven't seen any evidence of it whatsoever. It performs exactly the same as OPC mixes do. So good concrete practices, right? Placing, curing, weather, paying attention to the weather details, mix design, water cement ratio, of course, is prevalent, and of course the air void system, critical to good freeze durability.
All right, so it looks like that is all the questions. I'd like to thank you again, Nick. It was a very informative presentation. And we will be having our next meeting webinar for ACI Illinois, February 25th. Keep an eye out for the February newsletter, and there'll also be information posted on our website about that meeting. Thanks again, everyone.
Thanks for the opportunity, everybody. Have a great day. Be safe, everybody.
Thanks, Dan.